Hi everyone, welcome back to the Data Guy, your go-to channel for mastering data engineering tools and concepts. If you are new here, I'm Vishal and I create videos to help you build a strong foundation in data engineering. In part 1, we dove deep into cluster optimization, how to configure your clusters for maximum efficiency, save cost and supercharge your performance. If you missed that, be sure to check it out. But optimizing your database performance doesn't stop there. In this video, we are tackling the next steps that will help you fine tune your data pipelines, make the most out of Delta Lake. Efficient use of storage in Azure Databricks involves optimizing how data is stored, accessed, and processed to reduce storage costs and improve the performance. This is especially important for handling large scale data sets in a distributed environment. Now, first, let's talk about why storage optimization is critical. It all boils down to three key reasons: reduce cost. Storage, especially in premium Azure tiers, can get expensive. So optimizing how you store data saves money. Next one is improve performance. Faster data retrieval and processing means your jobs finish quicker, freeing up resources for other tasks. Next is scalability. With efficient storage, handling terabytes or even petabytes of data becomes a breeze without degrading the performance. Now, in Azure Databricks, you have several storage options tailored to different needs. Azure Data Lake Storage. It is ideal for large scale hierarchical data. It's scalable, secure, and cost efficient. Next one is Azure Blob Storage. It is best for unstructured or flat file systems, perfect for temporary or archival needs. Delta Lake, a game changer. It adds ACID transactions, schema enforcement, and time travel to ADLS or blob storage, making it highly optimized for big data workloads. Now let's get into the how. Here are the top techniques to make the most of your storage in Azure Databricks. First one is choose the right file format. Stop using text-based formats like CSV for big data. Instead, go for Parquet or ORC. Why? Because they are columnar formats that compress data efficiently, enable predicate pushdown, so only relevant data is read. Next one is optimize file sizes. So beware the small files problem. Too many small files can slow down the performance. Now, here is how to fix it. You can use Delta Lake's optimize command to merge small files, or you can use the Spark to repartition during writes. Now, why Delta Lake? Because Delta Lake does it all: ACID transactions, file compaction, data skipping, and even time travel. It's the Swiss Army knife of storage in Azure Database. Now, here are some other options like data partitioning. Partition your data based on commonly queried columns. This reduces the data scan and speed up your query significantly. Next one is compression. Always enable compression when writing files. For Parquet or ORC, use built-in options like Snappy. For text-based formats, go with gzip or bzip2. But remember, compression can add CPU overhead, so balance wisely. Storage tier optimization. Save cost by using Azure School or Archive tiers for infrequently accessed data and keep hot tier for active workloads. Automate this with lifecycle policies. For example, you can move old data to cold storage using lifecycle policies or automation scripts. Data lifecycle management. Implement lifecycle management to delete or move stale data. So here's a quick recap of the best practices. Use Delta Lake for big data workloads. Go with Parquet and enable compression for batch data. Avoid small files, merge them. Use partitioning and clustering for faster queries. Implement data retention policies to archive or delete unused data. So efficient storage usage is a game changer for your Azure Databricks workloads. By implementing these techniques, you will save cost, improve performance, and scale seamlessly. Now let's talk about partitioning best practices. Partitioning is critical when dealing with large data sets. It splits your data into smaller, manageable chunks, allowing queries to process faster. Proper partitioning improves query performance, reduces I/O, and ensure efficient use of resources. Now, here is where partitioning is important. Faster queries. Queries scan only relevant partitions instead of reading the entire dataset. Reduced I/O. Less data scan means lower storage and compute cost. Better parallelism. It enables efficient resource utilization across worker nodes. Scalability. It handles massive datasets as your data grows. Now think of it like organizing files into folders. When you need something, you go straight to the right folder instead of searching through everything. Now that we understand why partitioning is important, let's go over the best practices to get the most out of it. Now, choose the right partition column. So, how do you select the best partition column? Select high cardinality columns. Columns with a moderate number of unique values like dates, regions, or product categories work well. You need to avoid low cardinality columns. For example, gender, status. This creates uneven partitions, leading to data skew and poor performance. And you need to avoid very high cardinality columns. For example, unique user ID. This can lead to too many small partitions, increasing overhead and slowing down queries. Now, how to optimize these partitions? Now, what's the ideal partition size? What should be the ideal partition size of your partitions? So, optimal partition size for big data, like you can aim for 256 MB to 1 GB per partition. This balances parallelism with I/O performance. Or a repartition or coalesce, which you should use. So if the partition is too small, you can use coalesce to merge partitions. If the partition is too large, you can use repartition to increase partitions for parallelism. So other ways to optimize the partition size is you can use partition pruning. So partition pruning allows Spark to scan only relevant partitions instead of loading the entire dataset. Next is avoid too many small partitions. Small partitions like less than 128 MB can increase the overhead of task scheduling and metadata management. And next is balance partitioning with bucketing. If the partition key alone cannot achieve even distribution, consider bucketing to further split data within partitions. Now, here is the example. So you can see the query here it is used for bucketing. So basically, this query creates a bucketed table in Databricks using Parquet format. So here, by using cluster by, we can define bucketing column to distribute data. So you can see the query here. Next is avoid over partitioning. So over partition creates too many small files, which leads to high metadata overhead, increase task scheduling time. So what is the solution? You need to avoid using very high cardinality columns directly for partitioning. So Azure Databricks provides powerful tools to manage partitioning efficiently. So first one is Delta Lake partitioning. Delta Lake automatically handles metadata and partition pruning, compact files and optimize partitions using the optimize command. You can use the optimize command to compact the small files, and in this way you can optimize the partitions. Next one is dynamic partitions in Spark. Spark automatically detects the writes data into partitions. Next one is partition discovery. Spark automatically discovers partitions in nested directories. So no need for manual intervention there. Let's summarize this. Choose the right partition column, moderate cardinality like date, region. Keep the partition sizes balanced. So you can keep it like 256 MB to 1 GB per partition. Use partition pruning. Always filter by partition columns. Avoid too many small partitions. You can use optimize to compact the files. Balance partitioning with bucketing for better query performance. Avoid over partitioning. Too many small files can slow down the Spark. So partitioning is the foundation of a high performing ETL pipeline in Databricks. If you follow these best practices, you will see faster queries, lower cost, and better scalability. Now let's look at Z ordering and data stream management in Azure Databricks. Both Z ordering and data stream management are key concepts in distributed systems like Azure Databricks, where efficient query performance and balanced workloads are crucial. Let's dive into each concept. So why Z ordering and data stream management matters? In distributed systems like Databricks, unoptimized data layouts and imbalanced workloads can lead to slow queries and inefficient resource usage. Z ordering improves data locality, while skew management ensures even distribution of workloads. Now let's explore these concepts in detail. So Z ordering Delta Lake. Imagine you have a large data set and you frequently query it based on specific columns. For example, date, customer ID. Without proper optimization, Databricks might scan more data than needed, making queries slower. So Z ordering is a technique in Databricks Delta Lake that reorders data in a file to group similar values together, reducing the amount of data scanned during queries. You can think of it like arranging books in a library. If books are randomly placed, finding a specific one takes time. But if books are grouped by category, you can quickly find the section you need and pick the right book. So, how does it work? So, Databricks uses Z order curves, a space filling technique, to store related data close together. This helps in efficient filtering and speeding up queries significantly. So, when should you use Z ordering? So, if your queries involve filtering or where conditions on specific columns, Z ordering can speed up the performance dramatically. It's especially useful for large data sets in Delta Lake. So, how to apply this Z ordering? So, you can see in this on the screen the command. So, this is how you can use Z ordering. So, basically, this command optimizes the table and reorders the data, ensuring that queries on date or customer ID run much faster. So with Z ordering, you can reduce data scan size by 10 times or more, leading to faster queries and cost saving. So why use Z ordering? To minimize data scanning. It reduces the amount of data read during queries by co-locating data that is often queried together, particularly effective for range-based and multi-column queries. For example, if you query on date and customer ID, Z ordering on this column will make data for specific dates and customers more localized. Second one is to improve the query speed. By reducing the number of files or partitions scanned, queries execute faster. Next one is complement to partitioning. While partitioning organizes data hierarchically, Z ordering optimizes data within partitions. So Z ordering best practices. First one is avoid overuse. Z ordering is computationally expensive, so apply it only to tables or partitions that are queried frequently. Second one is use with time series data. You can partition by date and Z order by columns like customer ID or regions. Third one is compact files before Z ordering. So ensure files are compacted before Z ordering to avoid overhead. So Z ordering is powerful, but it comes with a cost. It should only be applied to datasets where it provides real benefits. So now look at data queue management. So imagine you and your friends are dividing a huge task among yourselves, but one friend gets way more work than the others. While most finish quickly, this one friend is stuck working alone, slowing everything down. So this is exactly what happens in Databricks when data is not evenly distributed across partitions. Some tasks finish fast, while other takes much longer, so leading to data skewness. So, what causes data skewness? First one is skewed by key distribution. So, when a small number of keys, for example, null or a popular value, dominate the dataset, some partitions are overloaded. Second one is improper partitioning. Partitions created using low cardinality columns can result in uneven data sizes. For example, partitioning on region when most of the data belongs to a single region. Third reason is data aggregation. Grouping or joining on skewed keys can cause imbalance shuffles. So, how to detect this skewed data? So, you can detect it by skewed partition sizes. You can use the Spark UI to check partition sizes. Skewed partitions will show significantly larger sizes compared to other partitions. Second one is straggler tasks. So, look for tasks that takes much longer to complete. Third one is query analysis. Examine group keys or join keys for uneven distribution. So let's look at some of the techniques to how we can manage this data skewness. So first one is sorting. Now we can use sorting. So sorting is basically adding a random number to spread data across multiple partitions. Second one is skew join optimization. If you are doing joins on skew data, you can enable skew join optimization in Databricks. So you can enable it by using this property here. Now, using this property, Databricks automatically handles skewed joins, making them way faster. Third one is AQE, adaptive query execution. So Databricks has this AQE, which automatically detects and fixes skewed partitions. So to enable it, you can just run this property here. Now, summary of the best practices, like analyze the key distribution, use distinct counts and distribution histograms to identify skewed keys, avoid low cardinality partition columns, choose partition keys with a uniform distribution, enable AQE, adaptive query execution in Spark. So monitor and monitor it regularly. Regularly review job execution plans to identify and address new key issues. So use Z ordering for efficient data clustering within partitions and manage skewed keys and partitions to ensure balanced workloads and avoid straggler tasks. By combining these techniques, you can achieve balanced data distribution, minimize the I/O, and significantly improve query and job performance in Azure Databricks. Finally, let's talk about collaborative development in Azure Databricks. So, collaborative development refers to multiple users working together efficiently within a shared environment to create, manage, and optimize data engineering, data science, or analytics projects. Azure Databricks offers various features to enable seamless collaboration. So the key features enabling collaboration in Azure Databricks are shared workspaces. Azure Databricks provides shared workspaces where multiple team members can collaborate in real time on notebooks, code, and workflows. Users can organize projects by creating folders for different teams or tasks, enabling logical separation. Second is real time collaboration in notebooks. So real-time editing, commenting system. So multiple users can edit a Databricks notebook simultaneously. So these changes are visible in real time, similar to Google Docs. And you can add comments to code blocks or markdown cells to share feedback, notes, or suggestions with collaborators. So comments are versioned and tracked, so ensuring clarity in communications. Third one is notebook revision history. All changes to a notebook are tracked with a revision history, allowing you to view, restore, or compare previous versions of the notebook. So this feature is particularly useful for rolling back unintended changes, auditing changes in collaborative projects. Next is Git integration. So Azure Databricks supports integration with Git repositories like GitHub, Azure DevOps, or Bitbucket for version control. So developer can clone repositories directly into Databricks workspaces. They can commit, pull, and push changes to sync local and remote versions. They can use branching and merging to manage different project development streams. And the best practice is use Git integration for long-term project management and version control. Next is RBAC or role-based access control. So here you can assign permissions at granular level, like you can assign permissions at various levels like workspace, folder, notebook, or cluster. Users can only view, so there are some uh, different permissions are there like view, run, edit. View by using view, user can only view the content, or by run permission, user can execute code but cannot edit it, or with edit permission, user can modify the code. So this ensures sensitive data and workflows are secure while allowing collaboration in appropriate areas. So next one is jobs and workflows for collaboration. So job scheduler, you can create schedule jobs for automated execution of notebooks or workflows. Team members can collaborate by designing workflows, monitoring job runs, sharing alerts and logs. So task dependencies, you can enable multiple users to work on different tasks within the same pipeline. Next one is cluster sharing. So teams can use shared or collaborative interactive clusters to test, debug, and execute code together. Configurable resources ensures users cannot overwrite or disrupt the cluster unintentionally. So last one is shared libraries. So teams can maintain and share reusable libraries like Python, Scala, or Java packages to standardize code and reduce duplication. You can manage shared libraries through Databricks Library UI or programmatically via API. So by leveraging these features and best practices, Azure Databricks enables teams to work together effectively, ensuring faster development cycles and better results.
Thanks for watching. If you found this video helpful, give it a thumbs up, subscribe to the Data Guy for more beginner-friendly data engineering content, and share this video with someone who is just starting out. Have questions or ideas for future videos? Drop them in the comments below. I would love to hear from you. Until next time, happy coding.